Hello, welcome back. And today I'm going to give some lecture on Markov chains and hidden Markov models. I'll give you the introduction and the motivation. Before I do that though, I want to review what standard ML is because a lot of us know what machine learning is and it's a good reference point to compare why we might need different models for different settings. For standard ML, we have some data, and here this is just like a classification problem. Got some images, and you want to learn a prediction rule based on some labeled images. And obviously, standard ML doesn't have to be labeled, it can be unlabeled, but so on. But you want to learn a prediction rule, and so on. So maybe if I had a new image, like a person, it'll predict that this is a person. This is like a classification problem. And why we want to review this is because just some of the properties, and to reiterate what like ML is really good at, and like the setting and all this kind of stuff, is that in ML we assume that our data comes from some distribution, but we don't know what distribution is, so we have to say that this is distribution free. And we also only work with finite samples, so we have to say this is finite sample guarantee. But more importantly, what I want to focus on is that our data is IID. So for example, a person data is independent from being an object like a pencil. But I asked the question, what if data can be sequential? There are applications like weather where you might track something, and this point here is definitely dependent on every single day or time or hour before it. Or things like in finance where we physically have stock markets, right? The rise here might be dependent because we had a rise here and so on, and we're in some kind of, what is it called? Bull market? I think so. But anyways, we can continue. So Markov chains is what I want to introduce and motivate. What if our data is not IID? And rather than assuming the full dependence, so for example, if we had some kind of data here, and rather than assume that this point here is dependent on everything before it, because then we have to know every single combination and store everything before it and so on, which won't be tractable, this uses something called the Markov property, that the probability of the next state is only dependent on the state we are in right now. And to give you some motivation that we actually use this a lot is, for example, in board games. Chess, we don't care how we got to this position, right? We don't care every single combination, and in fact, there could be infinite combinations got to it. We just care what is the best move given the current state. And if anyone's played chess, I like to move my rook here and checkmate. So board games, we like to use the Markov property if you do things like reinforcement learning and so on. So Markov property is very good because it saves a ton of parameters and it makes a problem a little bit more tractable. And how can we leverage this Markov property? Well, first let me introduce what a Markov chain is. It mathematically transitions from a state to state. So how do we model this? Introducing you the Markov model. And this is an example of a Markov model. Imagine you're a student who goes to school every single day, and they have uniforms, and they have to wear a shirt every single day, and there's different colors, red, green, and blue. Naturally, we don't want to wear the same shirt every single day, because maybe we have to wash it, so we might want to ask, given that we wore red today, what is the probability that we stay in the same state, which here is 0.3? Or what is the probability I go to a different state? Maybe I wear a green shirt tomorrow, that is 0.5, and so on. And we can track all these probabilities into something called the transition matrix, which is the probability that the next state goes to state, let's just call it Sj, given your current state. And notice that the transition matrix is actually has the Markov property there. And here we look at it in rows. So given I start in red, the probability I stay in red is 0.3 and so on. And each row will add up to 1. We also have something to keep in mind, is something called the start state. And it's like, okay, given the first day in school, this is the probability distribution that I'm going to be wearing different shirts. And I'm going to label this as red, this is green, and this is blue. And the reason why we have the start state is because we can do this fascinating thing where we can find the probability of the next day. So the second day of school, or I label as 1, so let's say the next day of school, the first day of school, given your start and state distribution, and you just do a row vector times matrix. And intuitively, this should make sense because the row vector is the start state for being red, green, and blue in each individual entry. And I'm only going to look at one column of the matrix, but this column is basically saying the probability of ending at red given I started in different colors. So if I do this vector times matrix multiplication, in each entry I'm going to get a dot product, and the first entry will be like the red at time 0 times the probability of staying in red, and green at time 0 times the probability of staying in green, and same thing with blue. So if I want to find, and I'll fill this in, the probability that my next state is red, all I have to do is this dot product, which will be 0.3, which is the start state of being at red, times 0.3, which is staying in red, 0.2 times 0.1, which is green, and 0.5, which is the probability of starting off blue, maybe blue is your favorite color, times 0.1. So that is basically what a Markov model is. Another example of a Markov model is every day in life, imagine there's only two states. You're either healthy or you're sick. And I like to motivate this example during COVID-19. So imagine during COVID-19 and the pinnacle of it, the peak, talking 2022 when everything was closed, you were either healthy or sick, and maybe 95% of the days you were healthy, but 5% of the time you actually got COVID and you got sick, and you stayed sick a couple of percent of the time, but then, usually you recovered and you went back to healthy, and you're either only healthy or sick. So how can I be more specific? Well, I'll just change sick to COVID. Like that. Voila. What's problematic though? Well, I didn't tell you this, but the Markov model assumes that you know every single state. You know that you're going to wear red because you can see it. But here, during the pinnacle of COVID, we couldn't actually see whether we had COVID or not. That's why there was those warnings. If you have these symptoms, please stay home and so on, right? We couldn't actually see COVID until we had COVID testing. Then you can kind of confirm here and there that you have COVID or not. So COVID is actually hidden. And sometimes you may have seemed like you were healthy, but you actually had COVID. And sometimes you seem that you may have had COVID, you had all the symptoms, but you were healthy. So we have to introduce a more complicated model. And this is where I think hidden Markov models become a lot more powerful, right? These Markov models are pretty good, but in the applications that we want, like weather, finance, and health, there's going to be a lot of hidden states. We're not going to see weather in the future. We're not, or we might not see like whether it's actually sunny or stuff like that. We just get information from metrics. Same thing with finance. Same thing with health. We can't see the diseases. We get some kind of information from scans, CT scans, blood pressure, vitals, tests, and so on. This is the crux of hidden Markov models and why they make it so powerful, because usually in most applications, we can't see some of the states. They're called hidden states. Coming back to the COVID example, what if we can predict COVID given some observable informations from our smartwatches? These smartwatches, they're pretty fancy. They can track temperature, HRV, lots of things, oxygen, something like that. I'm not too familiar with them, but they can get you a lot of observable metrics. Can you actually predict the hidden metrics based on that? This is how the hidden Markov model gets motivated, is that we see symptoms, not diseases. So we need a new problem now. We need a mathematical framework that can infer the hidden causes from visible observations, very key, over time. And why? Like, why can't standard ML do this? Well, standard machine learning predicts Y given X. But remember the IID assumption. What if we need to include time and hidden states? Now we have some dependencies involved, and we actually want to leverage these dependencies because they're very important. So many applications, standard machine learning won't be able to capture this, like forecasting weather, predicting hidden diseases, and to give you a different example, for example, heart attack. These watches can do a very good job at predicting heart attack, and they do this because of this whole time dependency thing, right? We can get all these informations on on like heart rate, beats per minute, and we can assess whether you may or may not have heart attack or not. So, what is the hidden Markov model? Well, the hidden Markov model has hidden states, and I denote my notation by capital S. Here in this example, we have COVID, healthy, and flu, and it has observable states. So hidden states you can't see, observable states you can. And remember how I said we can't see diseases, we can see symptoms. So here my observable states are none, chills, cough, and fever. The key thing is that the hidden layer is assumed to still be a Markov chain. Imagine you're only healthy, only COVID, or only flu, and you can't get the combination either. So you either always switch between either or, and you just keep switching. So this is a Markov chain, and we can label this by a transition matrix. The probability of the next state is only dependent given the current state, and this actually uses the Markov property. And it also has the emission matrix, which basically means what is the probability of the observed state given the hidden state. So given that I observed, let's say, none, and I keep observing none, what's the probability that I had COVID? Well, it's actually very rare that you have no symptoms, given that you have COVID, but the probability might not be zero, because this was the case. Or, for example, the probability that I observed chills, given that I had COVID, maybe this probability is higher. So the assumptions is that the hidden states are Markov. And now you might ask, okay, this is a really cool model. It's more informative. Like I like to say that it's way more informative than just the Markov model, because oftentimes we only have hidden states. Like we don't know whether we have COVID or flu unless we actually test for it. So what's the whole goal of this hidden Markov model? And then versus standard machine learning, what are our goals? What can we do with it? Well, we can actually do lots with it, and that's what I'm going to give you, and then I'm going to tell you the applications afterwards. Well, the first thing we can do is we can just first learn. Like, what if we want to learn the model? And this is very similar to machine learning in the sense that given a sequence of observations, so if you come back here, maybe you have a sequence of chills, 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 and maybe some of none states, learn the parameters that maximize the likelihood of the data. And this is very common and very similar to what you do in machine learning. It's literally in the name that you want to learn the model. Okay, the other thing we can do is something called inference. And when we mean inference, we really mean is like, given the model now, can you infer things out of it? So given the model, how likely is that observed sequence? So say that you have the model and you observe a sequence of like chills, 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 chills. Now, how likely is that sequence given that model? Maybe the model to get to chills was very low, and it wasn't likely. And this is very useful because if this is an abnormal case, we might want to flag it and give it to a doctor saying, hey, we got some kind of weird thing coming out of our model. The other thing that becomes very useful, and I'll show you why, is something called decoded, another inference technique. Remember, given the model and a sequence of observations. So maybe we have like none, and chills, and so on, and then we have none. Can we find the most likely sequence of hidden states? So when we had that sequence and we had a bunch of chills in the middle, maybe the sequence of hidden states is not normal. Maybe you actually did have COVID. So this also becomes very important. But rather than showing you all this math and definitions, let's just show you examples of why these predictions and these different settings compared to standard machine learning is very useful for different types of data that have this dependency. First thing we want to focus on is past predictions, saying that we observe things and now we want to predict things from the past. And you might be asking, how is this useful? Don't we always want to predict in the future? Why do we want to care about the past? Well, that is a very good question, and I will answer that right now. If anyone's had these wearable devices, people are obsessed with something called sleep score because they can track sleeping and they can predict how good your sleep is, how bad your sleep is, and maybe we can use things to like predict sleep apnea. So this application is motivated from a research paper that I read from my professor. I will link his YouTube and the paper. I highly recommend you to check those out and subscribe to him as well. Basically, given your observations, and we can say your smartwatches, and I'll say it right here, it can track maybe like your EEG and your coordinates. So what if you move around a lot in the night? Maybe your sleep wasn't good. You want to predict actual sleep stages that medical professionals and sleep professionals have characterized. And these sleep stages are awake. Now, these are called NREM, which I won't get it too much in the details because I am not an expert in this. But N1 basically means light sleep, N2 means a little bit better than light sleep, but maybe kind of light sleep, and N3 is like deep sleep, like the one that you actually want. And then you can have REM sleep, which is like dreaming. I don't know if REM is what you want, or REM is dreaming or not, but REM is sleep or not. But anyways, we can use decoding to find the most likely sequence of hidden states, so this is on the past, to predict abnormal sleep transitions. So imagine that you observe really good coordinates and EEG and all this kind of stuff, and the most likely sequence was actually like you were awake sometimes, and then you went to light sleep, and then you went to this, and your transitions look very normal. So maybe your sleep score is very good. But what if you like switch between awake to light sleep and each state gets observed every 30 seconds? So maybe not every 30 seconds you're awake and then you're light sleep, but maybe every 30 minutes you're awake and then you go to light sleep and you never actually hit the deep sleep. Then here we can predict that you probably had a bad sleep score, and we might be able to even extend this further to maybe predict things like sleep apnea. So this is how it gets very useful, that you can use wearable devices that track observations that you can see to predict states that you can't see. And this is like the main motivation of hidden Markov models. Well, not motivation, but a really good application. Another application is when you want to predict GPS tracking. Imagine that your observations are these noisy GPS signals from satellites, and you want to predict the actual state, like the actual street that you're on, that you're driving. Well, if we just used just your data, it would look like this, and it would cover a lot more distance. So here we want to actually find the most likely state to correct abnormal locations, meaning that your observations look something like this, and maybe you had an observation here, here, and here. Well, then clearly your actual state is this street here. We'll call this maybe like a 111 street, and we want to smooth this out so it can make GPS tracking more accurate. It's just another application. I like to call this application smoothing. Another thing you can do is you can predict the present. I'm going to go a little bit faster here because I just want to show you the applications. But if you're a robot, and you're going around in this makeshift room with walls and stuff, and this actually works in self-driving cars, but maybe self-driving cars actually know their locations, but these robots don't. They don't have these like satellites to actually tell them accurate locations, and the only way they can read their location and the current coordinates is by bouncing off sensors off walls to kind of give them an idea. Well, clearly these sensors are going to be your observed state, and what you want is you want to know your present state, your current coordinate, and we like to call this filtering. I'm going this a little bit fast as I just want to show you the applications and the motivations. And I alluded this earlier where you can do future predictions like forecasting. And forecasting is very much related to weather forecasting. So have you ever seen the weather news where it's like Monday is going to be this, Tuesday is going to be this, Wednesday is going to be this, Thursday is going to be this, and each day it's like sunny, and Tuesday is like sunny but with some clouds, and Wednesday it's cloudy, and Thursday it's windy, and so on. Well, you can have all those as actual states. Your observations aren't rainy, sunny, snowy. These are hidden. Your observations are the sensor readings, like temperature, wind, and so on. So you can predict a sequence of future states given your observations. I hope this video kind of shows you why different type of settings, like the different type of model settings, like hidden Markov models, become very useful when our data, we go back up, is not IID, and our data is dependent. Thank you.